Hi again everyone. In this video we're going to learn how to solve polynomial equations that involve complex numbers. Now at school you would have solved equations like quadratic equations, but when complex numbers are involved, firstly you need to recognize that equations involving complex numbers can require more care to solve, so a little bit more care and detail is required. But why would we want to solve these equations? Well, in the analysis of applied problems, we often need to solve equations. And the solutions, hopefully, are the desired information that we seek. Knowing how to solve polynomial equations with complex numbers just adds to our repertoire. So it's very powerful. Let's build our intuition though. How do we actually solve these types of equations? Here we're asked to find all of the complex fourth roots of this complex number here, and you may leave your answer in polar form. So let's just write out the actual equation that we are endeavouring to solve here. And of course we want to solve this for z. Now, the fundamental theorem of algebra tells us that because of this power 4, we would expect 4 solutions to this equation. So it's our task to go through and extract those 4 solutions. How do I do that? Well, I'm actually going to write the right-hand side here in so-called polar form. So now, polar form of a complex number involves a length, r, to the origin, and an angle, theta, where theta is the angle to the positive real axis. So what we would like to do is calculate a specific r and a theta for this right-hand side. Okay, well, we can easily do that. Now the 8 here doesn't change anything. Usually to find the r, you square the coefficient, I guess each component here, and add them together and take the square root. Now the 8 isn't going to, you can expand these, but I'm just going to leave the 8 out there for simplicity. Okay, so simplify here and we'll get 16. Next thing we would like to calculate is the theta associated with this right-hand side, this complex number here. Well, theta is just tan inverse root 3 on minus 1. Okay, so again the 8 isn't going to change anything here. Now, this complex number here is going to lie in this second quadrant. Now, what I can do is draw a little right-angled triangle and then use basic trigonometry. So if this angle here is alpha, what I'm interested in here is the theta there. Okay, so simple trig using the tan inverse will give me alpha equals pi on 3. So theta then will give me 2 pi on 3. So combining this and this, we can now solve the following. Now how does this help us? Well, we can take the fourth roots of both sides and then simplify. Now, this is where it gets a little bit tricky. You can just use your index laws here, and if you wanted to, you could expand this, but there's a danger there. If I expanded this, I would get one value for z. But again, by the fundamental theorem of algebra, we would expect there to be 4 solutions here. Whereas if I just expanded this, I would only get one solution. So what can I do? Well, a good idea is to use the fact that this complex number can be produced by going out and spinning around 2 pi radians around the origin. So I can actually write it like this. Plus, I guess, I 2 pi k. Now where k is 0, plus or minus 1, plus or minus 2, etc. Okay, now what I'm going to do now is simplify this and then expand as I normally would. Okay, so I should have something like this. And then let's bring that quarter in and simplify. Okay, so now we're in a position where we can just substitute in various simple values for k, and we will get different roots for our polynomial. Okay, so let's try the simplest one. If k equals 0, then I'm going to get, I'm just going to put a subscript here to note that this is associated with the k equals 0 value. So this disappears and I get I pi on 6. Let's choose another one. K equals 1. I'll go up here, I'll add these together, get 4 on 3 and then simplify. And I should get something like this. Okay, that's another one. So let's keep on going. Let's do k equals minus 1 now. I guess this should be lowercase. So I go up here, I substitute in k equals minus 1 and simplify. If I do that, then I'll get the following. And finally, well, I could put in positive 2 there, but I'm actually going to put in negative 2. And you'll see why in a minute. Okay, now the important thing here is that these coefficients of I should be strictly greater than minus pi, but less than or equal to pi. Okay, if I put in k equals positive 2 in here, then I wouldn't get that simplification. Okay, so I've got 4 roots here. I've solved the equation. They're all in polar form. What I'm going to do now is just plot these complex numbers on a diagram. We're not asked to do that, but I think it's important anyway. So I'm going out 2 units. Okay, and I'm going to plot my various solutions. So I'll go 2 units and rotate anti-clockwise pi on 6 radians. So that would be Z0. Then I go out 2 units and rotate 2 pi on 3 radians. So this would be Z1. Again, I rotate pi on 3 in the clockwise direction to get Z to the Z minus 1, and keep on going to get Z sub minus 2. Okay, so let's look at the bigger picture. basically, what are some ideas that you can use to solve all sorts of problems? Well, this approach involved the polar form, and it's probably the easiest and the most elegant method for finding roots of complex polynomials. Although you can use an alternative method for solving quadratic equations, and I've got an example down here that I'm going to ask you to do. Sketching the solutions can provide some geometric insights into the problem and its solution. Now, a good piece of information here is that always remember, you don't get good at mathematics unless you do mathematics. You need to learn by doing. So I've left some examples here for you to do to further build your knowledge and your intuition.